Okay, good morning. It's hour 35 of topics in knot theory. So the goal for the remaining two classes is to say a little bit more about UVW braids. So U means usual, V means virtual, W means W, but maybe also welded or some other things. And we started talking about them last time, and then prove that the group PWB has a Taylor expansion. But of course, first I'd have to define what does it mean for a group to have a Taylor expansion. But even before that, I would like to apologize about unique factorization. So let me switch to a handout I made about it, and which I will also post on the class website. So in the class more than a week ago, I made an assertion that was wrong, and furthermore I couldn't fix it. So I'm not quite sure what to do. So actually when I taught about unique factorization before, I was using a completely different proof, and for all I know it's still right. But this time I decided to follow a proof by from the book from Licorice, and I failed. And I still don't know how to fix it. So, I don't want to go through the proof last time, from Friday, because it's too involved. But let me just say what was the failure. So the failure was, at some point, we had the black disk, and it was intersecting the the black ball B, and it was intersecting the green surface, S2 sigma. And we had an intersection of the following form. So basically there was an intersection which looked like an annulus. So these two lines go around. So there is an intersection like this, union this, which is an annulus. And I suggested to add a disk down at the bottom, and then that divides the original ball B into two balls. One is sort of, I'm highlighting it now, and the other one is its complementary. And I said one of the two balls contains a prime factor P. So you take that one and you reduce B to be that ball. But this is wrong, because if you end up replacing B by V1, so V1 is the funny ball that looks like this, then you are not reducing the number of intersections. So you need to argue in a different way. And if you look at how Licorice argues, he argues in a different way, and here is the precise line in Licorice that I failed to understand. I'm not 100% sure if this is my failure or a problem with Licorice. After that in Licorice comes a very mysterious paragraph, which I actually do understand, so you're welcome to go and struggle with it. Anyway, at the moment I'm not sure what to do about it, and going back and proving it the old way that I used to know is not an option anymore, because I spent too much time in this direction and I can't. So at the moment the theorem remains unproven in as much as this class is concerned. If I'll figure it out by Wednesday, I'll say something about it. If not, and likely not, then sorry, don't know what to say. Okay, anyway, so let's go back to class material. So, okay, so back to groups, sorry, so to braid groups. So just to remind you, the pure usual braid group, and I'm suppressing the subscript n for the number of strands. So the pure usual braid group, or often the u is suppressed here because it's the usual, is the kernel of the map from usual braids to the symmetry group. We talked about it. The pure virtual braid group is silly braids. So you start from a completely incorrect way of presenting the braid group. You write a presentation, here it is, and then you realize, ooh, that was a stupid presentation, but maybe the group is interesting. So you get this group, and I'll talk more about it in a minute. So it's the group generated by sigma ij, where I stands for where sigma ij stands for strand I goes over strand j with a positive crossing. The relations are a Reidemeister 3 move written here, and basically that things that are far away from each other commute, and in both relations the assumption is that all the indices are different from each other. And the name of this group is pure virtual braids, and I still owe you an explanation of more about what it is. Okay? But even before that, we looked at the quotient of pure virtual braids by an additional relation, sigma ij sigma ik is equal to sigma ik sigma ij, which is often called Overcrossing's commute, or OC. And the quotient group is called PWD, which is pure virtual braids. And I started interpreting it last time, and I want to finish the story. So it's the group of horizontal flying rings. And I should say that the word horizontal here is not crucial. If I wanted to extend the group to allow non-horizontal flying rings, so rings that could flip over, for example, it would be a minor extension. It would require a tiny bit more effort, but it's not a big deal. We're mostly talking about flying rings in R3, and as I mentioned, flying rings in R3 just means rings that fly around, so long that as they're external to each other, they live in a simply connected space, so you can think of the whole space in which they are external of each other as the base point for the purpose of computing the fundamental group. But then the generators are when strand j flies through where ring j flies through rings I. Okay? And so here is the generator. String j flies through ring I, and it's a positive crossing. Sigma ij inverse would be with a negative crossing. Now what does a positive crossing mean? So if you think of string I, well, you can it bounds a disk. This disk is oriented. This disk is oriented. Now also ring j flies through a certain path, and then the triple defined by, well, okay, or you know what? This at the crossing point here, you have a right-hand law. You have a right-hand law with which you can decide whether this was a positive fly-through or a negative fly-through. So basically you hold the trajectory of strand j with your right hand, and then your fingers either spin with the orientation of the disk, which actually also mean with the boundary of ring I, or they don't. And that decides whether they're positive or whether that was a positive fly-through or a negative fly-through. It remains to check these relations, and let me check it very brief. Sorry, it remains to check all relations, so 1, 2, and 3. So let me do it very briefly. So relation 2 is not worth checking, so I will skip it. Basically it means you have 4 rings and they're far away from each other, and the relation says that it doesn't matter whether this one, the one on the left, whether this flies through that one or this one through that one. It doesn't matter which two. Well, I said too much. So let's do the other 2 relations. So first of all, actually Overcrossing's commute is a bit easier. So suppose you have a ring I, so this is ring I, and there are 2 rings J and K that want to fly through it. So J flies and K flies, and topologically it doesn't matter in which order they fly through, and the 2 orders are exactly sigma ij, sigma ik, and sigma ik, sigma ij. So that was easy enough. So that was a proof of relation 3, and now let's prove relation 1. So proof of relation 1 is, so now I have, oops, sorry, I should have left a gap. So now I have ring I, ring J, and ring K, and ring K wants to fly through J and then through I, and ring J wants to fly through ring I. There is a midpoint. The midpoint is where they're all nested through each other. So you have I, and then J, and then K. And but then there, which basically means that sort of all 3. So K. So the whole picture telescopes into this picture. So K and J simultaneously fly until everything is nested this way, and then they continue simultaneously flying, where K is flying a bit faster, so that at the other ends, at the other sides, they split with K at the top and J in the middle and I at the bottom. Okay? But it also but this can also be done in steps. So either first J flies through I, this is sigma ij, and then so now J is above, so K can fly through I, so this is sigma ik, and then K flies through J and it's on the other side. Or, well, first K flies through J, then K flies through I, then J flies through I. And the 2 are homotopic via the middle path, where they all fly at the same time. I don't know, I hope this is sufficiently clear. Is it, or should I? Okay, good. So it actually requires a proof that these are the only relations, but I will not do it. So for me, this is the definition of PWB. Also, I should say that this is the beginning of the contact of what we're doing with 4-dimensional topology. Because, you see, just like a motion of points in the plane is really one-dimensional strands in R3, so is a motion of rings in R3. If you think, or if you include the time coordinate, it becomes knotted tubes in R4. So knotted two-dimensional surfaces in R4. And the story goes on. So this could be a beginning of a discussion of two-dimensional knots in R4, except we're not going to go there because the semester is ending. Okay. But what else did I want to say? So I wanted to say more. So I sort of told you what is PWB. But now I want to tell you a little bit more about what is PVB. And to tell you a little bit more about PVB, maybe I should start with a tiny chapter on so-called virtual knots. So, what are virtual knots? So first of all, maybe I should say, what are knots? Okay? So one definition of knots, or maybe it's knots and links, okay? I mean, when I say knots, but I really mean knotted objects. So one definition of knots is graphs with certain properties. So quadrivalent graphs, planar quadrivalent graphs, appropriately annotated. So what do I mean by that? Well, okay, sorry, I was going to draw a knot, but that was a fail. So, well, you see the graph. Here is the graph, right? It's quadrivalent, meaning that the vertices, so this graph has 4 vertices, one here, one here, one here, and they are annotated. They are annotated by saying which strand goes in, which strand goes out, also which pair is above, which kind of pair of opposing strands are above, which pair of opposing strands are below. You know, I could be technical, I could draw that, I could say in full detail how it is annotated, but it's pointless. It's clear from, you've seen these pictures. Sorry, these are not knots. These are knot diagrams. To make it knots, you mod out by Reidemeister 1, 2, and 3, which are local relations on the graphs. So basically, if you have 3 vertices which are annotated in certain ways, you can replace them by another triple of vertices that are annotated in the same way. Well, not the same, in some way that is derived from how these were annotated. Again, I could be formal, I could say it in full detail, it would be a waste of your time. Okay? So, these are knots. Now, what are virtual knots? This is great that I have copy-paste. So, let me circle all of this. Hit copy. You know what? Sorry, I'm going to be a bit fancier even. I'm going to shrink this. Oh no, sorry, I tried to be too fancy. I'm going to shrink this, put it on the side. Now copy it and paste it so that we have a parallel definition. And now I can complete the parallel definition. Now I want to define virtual knots. So virtual knots is exactly the same, except you delete the word planar. So the graphs are abstract quadrivalent graphs with the same annotations. They are they're not embedded in any place. They are on their own, okay? And you mod out by the same relations. It's a completely abstract construction. Okay? I'll explain it a little bit and then tell you why it's interesting and how it relates to our context. So first of all, there is an alternative way of thinking about it, which is somehow morally wrong, but also people find it easier to manage. Sometimes, I don't. Okay, so here is a morally wrong definition, or morally wrong equivalent definition. So basically, so let me give you an example of a virtual knot. So a virtual knot would be, here is a picture. So it would be like the trefoil, except this is a two-crossing virtual knot. The two crossings are here and here. So it's a quadrivalent graph with two crossings. Except out of every vertex come out 4 edges. So out of this vertex come out 4 edges. Maybe I'll kind of emphasize that it's a vertex by making it a bit tighter. So out of this vertex come out 4 edges, and out of these vertex come out 4 edges, and the output edge from here is connected to the edge from here of the other vertex, and the output edge from here, the edge exiting this vertex here, is connected to the edge exiting this vertex here. Okay? And the thing over here, which you might mistake to thinking, which by mistake you might think is a crossing, is not at all a crossing, it's a nothing. Okay? As a graph, it's not a part of the graph, it's just how the graph is displayed. Okay, when we draw the graph in the plane, we are forced to draw it in a way that has that has extra intersections. In graph theory, you see it very, very often. I mean, think of the what is it called? Sorry. K5. You know what? I don't know why think of the graph that has 5 vertices. What am I doing? Think of the graph that has 5 vertices and all possible edges between them. So here is a drawing. I'm missing one edge. Okay. This is a graph with 5 vertices. The things in the middle are not vertices, or just an artifact of the projection. Okay? So the picture shown here is a two-crossing virtual knots, and this is not a vertex. Not a vertex and not a crossing, and it's just a projection artifact. A projection artifact. However, the equivalent definition is to say, let's lift this to have a status. So let's call this vertex So let's think of it as a new graph in which this is a vertex, and call this a so-called virtual crossing. So it's not really a crossing. Okay? And then the definition will be, so the new definition will be, so virtual knots will be planar graphs, so planar diagrams with two types of crossings, two types of things, and these things are called regular or honest or classical and virtual. And then you mod out by relations that say virtual crossings don't really matter, aren't really there. You might as well have said in advance that they aren't really there. But instead you put them in and mod out by the relations that say that they aren't really there. So what are the relations? Okay, we have Reidemeister 1, 2, and 3 as before. We have relations that say that you can move virtual crossings across each other at no cost. So you have this is equal to that, you have this is equal to that, and you have this is equal to that, and these are called virtual Reidemeister, well, the order I wrote them, 3, 2, and 1. Okay? And then you have yet another relation, the so-called mixed relation. So this quotient line continues to the next page. So the so-called mixed relation, which says if you have an ordinary crossing and a pair of virtual crossing coming underneath it, you can replace it by that same ordinary crossing and the two virtual crossing coming the other side. This sort of means that basically, well, this implies that you can move the edges as you please across anything. Okay? So they're not in the so the virtual crossings don't really matter. But then there is a funny relation or non-relation in addition. So let's call it F, and F stands for forbidden, because it's actually not a relation, and it's a very, very funny relation, or very, very funny non-relation. It says that if you have a pair of crossings and a single virtual crossing, then this is not the same as that. Now you could say, wait, this is confusing. If the crossing here doesn't exist, if this is a virtual, if it doesn't exist, then who cares if you go underneath it or above it? Anybody knows? Well, the answer is, indeed, I could not care less about this crossing. This crossing genuinely doesn't exist. But these two graphs are different as seen from the perspective of the things that do exist. So they differ as they are seen from the perspective of the two crossings that do exist. So let me annotate it a little more. So let me orient everything and give names for the strands, at least just so that I can refer to them. So this one is z, and this one is z, and let's say this one is x, this one is y, and the same on the other side, x and y. And let me tell you the story on the left and the story on the right. So the story on the left, told from the perspective of z, so story as z tells it. Sorry, it. Sorry, as z tells it. So on the left, z says, I go under y, then under x. Okay? I go under y, then under x. On the right, z says, I go under x, then under y. I go under y, then under x, on the right it's first x and then y. So under x, then under y. So these are completely different graphs, even disregarding the crossings that doesn't exist. Okay? Sorry for the confusion, but this is the language that everybody likes and I hate. Okay. Anyway, so why should we care? Why should we care? Why should we care not about this definition, but about the definition, well, any definition, but in particular the definition I like? Yes, Leonard.
So the relation that Reitmeister 2 in the definition of the virtual knots, you said that, is it the same as the usual one?
Yeah, but I call it virtual Reitmeister 2. It's the same, except the two, it involves two virtual crossings, not two honest crossings.
So if someone has undone the virtual crossings and come up to two parallel lines, and then we have two good crossings and a Reitmeister 2 move, how do we tell the difference?
I am not sure what you're saying. Perhaps you are saying that this is equal to this is equal to this.
Yes.
And you are right. This is equal to this, is equal to this in the world of virtual knots. Because in the world of virtual knots, these, in my view, these two are literally the same graph pieces. Both of them have two edges and no crossings. They are literally the same. Okay? And in the other viewpoint, these are different, but they differ by a relation. Okay? Anyway, why should we care? So, well, maybe it's not really, I don't want to say why should we care. I want to say many knot invariants, their definition has nothing to do with planarity. So, if you think of the Kaufman bracket, the Kaufman bracket is defined by doing certain things to the graph, but whether the graph is planar or not is irrelevant. So the Kaufman bracket extends to the to virtual knots equally well. Okay, and many other invariants similarly. So Wirtinger presentation. The fundamental group of the complement as such does not mean anything for virtual knots, because the complement does not mean anything, because virtual knots are not embedded anywhere. Okay? They're abstract graphs, so they don't have a complement. However, there is a Wirtinger presentation. If you think about the Wirtinger presentation, it's just one generator for each arc and some relations at the vertices. The Wirtinger presentation makes sense just as well for virtual knots. So many knot invariants actually extend to virtual knots, and in some sense their more natural domain of definition is virtual knots. Though, yeah?
So then this version of the Wirtinger presentation, it will actually be the fundamental group when you look at that, the G-genus surface thickening interpretation of virtual knots.
Right? Yeah, but you need surfaces modulo some stabilization, and in fact to get the Wirtinger presentation you need to fill in the surface from the inside or from the outside. So yes, the Wirtinger presentation is at the end pi1 of some space or spaces modulo equivalence relation between some spaces, but nevertheless there isn't a knot complement. Okay?
Right.
Anyway, but I do want to make a few. I'll say it and leave it as a mystery because I really don't have time to go there. But for example, so generally speaking, you can ask, who cares what is the domain of definition of a knot invariant? So suppose the Kaufman bracket can be extended to something more. Who cares? And the answer is that if you think, for example, at finite type invariants, so when we talked about finite type invariants, it not only the individual knots mattered, but also the set of all knots. So finite type invariants were polynomials on the set of all knots. If you change what a knot means, if you extend the definition of a knot, you get a different collection of finite type invariants. So there is actually a theory of finite type invariants for virtual knots, and it's not the same as the theory of finite type invariants for ordinary knots, and it has its advantages and disadvantages, and I really can't go there. Okay, but I do want to say a few things. So in many ways virtual knots are the same as ordinary knots, but in other ways they're different. So here are some differences. So first of all, for ordinary knots, long knots are the same as, so if you note a long interval, like if you do this, so this is equivalent to knotting a circle, right? Because you can close a long knot, and then on the other hand you can open a circle, and it doesn't matter where you open it. So this is not so for virtual knots. So there is a map from long Vknots into S1 Vknots. This map exists, but it's not an equivalence. There is no opening up map, because the different ways of opening do not give you equivalent results. 2. So ordinary knots are a monoid, but virtual knots are are not an abelian monoid. Abelian monoid. So if you had two classical knots, so if you had two, in fact, let's make it long knots. So if you had two classical long knots, you could compose them and get one long knot. And in fact, this would be abelian because there was a funny argument where you shrink K1 and let it travel through K2 and come out on the other end. This argument fails for virtual knots. This operation of shrinking K1 and passing it through K2 and then expanding it once again does not work for virtual knots. And in fact, one way of seeing it, maybe the easier way to see it, is actually to use the perspective that I don't like. So, to use the perspective I don't like, you do the following, or you see the, so suppose you have a K1 and it has in it somewhere a virtual crossing, and you want to slide it under some crossing in K2. So you need to slide it over and under all the crossings, right? You need to slide K1 over and under all the crossings of K2. But you cannot slide a virtual crossing under an ordinary crossing. This is precisely the forbidden move. This is precisely the forbidden move. You cannot slide a thing that has virtual crossings through, under, or above a classical crossing. So it's not an abelian monoid. Similarly, there are two mirrors. So for a classical knot, there is a mirror image which is obtained by flipping all the crossings, or alternatively by flipping the orientation of the plane. For virtual knot, the two are distinct. Okay? And finally, there are, well, I told you that there is a fundamental group of the complement, that there is pi 1. I lied to you. Well, I didn't lie, I understated. So actually there are two pi 1s. So you see, when we wrote the virtual presentation, the Wirtinger presentation, the Wirtinger presentation was written using, well, we take the base point to be above the knot, and then the generators go under the strands. Now, there is also an opposite Wirtinger presentation. The opposite Wirtinger presentation is where the base point is behind the knot and the generators go above the strands. Now, for the two groups are isomorphic in the classical case because you can slowly rotate the picture. You could rotate the knot while not changing, without changing it, while at the same time moving the base point all the way around, and thus the two, and that takes one presentation to the other. But for virtual knot, you cannot rotate the knot. You cannot rotate the knot for the rotation is a geometric 3D operation. It does not make sense for abstract graphs. Or said in the forbidden move language, if you rotate a virtual knot, eventually you will have to pass an ordinary cross. So if you rotate this, eventually, if you rotate it, eventually this line will have to come across the virtual crossing, and this is forbidden. So these are funny. Okay. So that was an extremely quick and insufficient introduction to virtual knots, but now let's talk about virtual braids. So what are virtual pure braids? So basically I want to go from or define from sort of the same way as you define from knots, virtual knots, I want to go from braids to virtual braids. Okay? So what are virtual pure braids? Or you know what, let me skip it and talk about what people call virtual braids. Drop the word pure. And then talk about pure a moment later. So what are virtual braids? So let me use the definition I don't like. Okay, the truth is that I just don't like virtual braids. I like virtual pure braids, but not virtual braids. So let me do what I don't like. So what I don't like is to say, okay, it's braids just as before, except occasionally there is a virtual crossing. A virtual crossing is a crossing in which you just don't bother to indicate the sense, whether it's over or under. And then there are more relations. So modulo relations, and everything is always going up. But now let's turn it into algebra. So VBN will be the group generated by two types of crossings. So gamma I, which are ordinary, and tau I, which are virtual. Modulo relations. And what are the relations? So the ordinary crossings satisfy the ordinary Reidemeister relations. So what were there? Gamma I plus 1, gamma I is equal to gamma I plus 1, gamma I plus 1, and gamma j is equal to gamma I if I minus j are, if I and j are far away from each other. The virtual crossing satisfy the same relations. So also the Reidemeister moves. So tau I plus 1, tau I is equal to tau I plus 1, tau I plus 1. Also the second one, so tau I, tau j is equal to, I will not write it. And then a third relation, namely Reidemeister 2. Reidemeister 2 was not written for ordinary crossings because for ordinary crossing it was gamma I times gamma I inverse is equal to itself, is equal to the identity. For taus, it's just tau I squared is equal to 1. So tau I squared is equal to 1. And finally, there is a a mixed relation. So this is equal to that. That's not the forbidden move, that's the allowed one, that's the mixed one. And you can also write it, and it's, what is it? It's tau I gamma I plus 1 tau I is equal to tau I plus 1 gamma I tau I plus 1. And then there is another relation like the non-interesting relation, but mixing gamma and tau. So tau I gamma j is equal to gamma j tau I, provided they're far away. So if I minus j is greater than 1, and I think that's it. That's a whole mess, and next time I will show you that you can reduce it by a lot if you switch to the pure group, which we already wrote. So this is really the pure virtual braid group on n strand, semi-direct product, the symmetry group. Adding the permutations or making it impure is just taking the semi-direct product with Sn. Okay, I'm already 2 minutes late. I'll quit. I said too much. Hopefully see you on Wednesday. I don't know how much of the Taylor expansion I'll succeed to do, but see you on Wednesday. Okay.